Hello, welcome to chapter 4, your dynamics chapter. So in chapter 4 and 5, we are going to look at the laws that govern forces in our universe, in our known universe. We can use forces to explain lots of stuff, mainly stuff that you have learned to describe in your kinematics chapter. So you're going to start off here with this photo. You can see this person is smiling, but unfortunately he is kind of like being whacked in the head with a football. Okay, so there are a lot of things happening here. I can explain all of the 3 Newton's laws just based on one picture, but instead of going in too deep, I'm going to start from the very beginning, which is Newton's first law, and join us for the ride. Alright, so here you can see that we're going to move into dynamics now, move out from kinematics. So in dynamics, right, we will study the effect of forces on the motion or movement of any masses. So we learn to describe these masses in kinematics. So now we are going to talk about what causes them to move that way and what governs that movement. So first we're going to start with mass. Mass is a property of an object that resists change in motion. Now, for example, you can see there's an elephant here. So if it's a large mass, it's just difficult to move, doesn't want to move, resist the change. If it's a small mass, if a large mass is heading towards you, also difficult to stop. You know this, right? So this is what we call inertia, which is the reluctance of an object to change its state of motion. So think about it this way. The larger the mass, the more you don't want to change. So mass is actually, in physics, is known as an inertial property. Okay? It's known as an inertial property. And hence, here is your Newton's first law. An object will remain stationary or continue at constant speed unless constant speed in a straight line, okay? Unless acted on by a resultant force. Okay? So as long as you have a resultant force, or specifically an unbalanced force, okay, it must be from external, okay, some external resultant or external unbalanced force. Then the object will begin to change its motion. The TLDR version of this sentence would be: an object maintains its state of motion unless acted on by an external resultant force. So always think about the question this way. If we are talking about mass, it has to do with not wanting to change. The larger the mass, the larger the inertia, the more whenever you want something to change, it goes like, no. It's called the stubbornness of everything. So I know in chemistry you define mass differently, but in physics we talk about mass as a property of an object that resists change in its motion. Okay, so keep that idea in your head. An object that is moving will continue to move in a straight line, or an object that's not moving won't suddenly move unless acted on by an external force that you can identify. So for example, now I'm talking to you at about 10 p.m. in MCKL campus. If let's say suddenly something begin to float behind me and then you don't see anybody or any hand, that's the time that I should go home right? So that's the same idea So something that is not moving wouldn't suddenly move, and something that is moving won't suddenly stop. So for example, if you have a ball rolling across the Mabel Marsh Hall at a certain speed, if for no reason, right, you don't know why the ball suddenly changed direction, or even worse, the ball suddenly stopped, wow, that one also means time to go home. Stop. It's time to stop for the day, go to bed. You are hallucinating. So an object wouldn't suddenly change its motion unless there's an external force, and the larger the mass, the larger it is to change its motion. Okay, so put that in your head. And now we're going to talk about what this external force actually is. Okay, so a lot of times, right, whenever we talk about forces, we're talking about, don't really know what you're talking about because you can't see the forces, right? Okay, so when we talk about this force, by the way, I just highlighted all the keywords, what it means to maintain its state of motion. So now we're going to relate that to force. And force here, okay, is known as the push or pull. There's only 2 ways to exert a force. You either push or pull, okay? So that causes either a change in motion, which is where we will focus our study on, especially for chapter 4 and 5, okay? So causing its state of motion to change, okay? But we also know that force have other things lah, right? So when you say change the motion, it means to accelerate. Okay, so all the yellow one, reluctance to change, don't want to change, want to maintain state of motion. This one is, the yellow one would be no resultant force lor. Okay, let me toggle a bit. Okay, we're back. So here you can see this is what I mean by changing the state of motion. If you have a net force, the motion will change. If no change, it is described with this word: reluctance of an object to change its state of motion, remain stationary, continue at a constant speed at a straight line, etc., etc. Right? So now, when we talk about forces, right, it means the push and pull of an object, causing it to change its motion. So if you look at the handy dandy little diagram I found for you, you can see this is an example of a car, and the car have 3 different states. This D here is your drag force, okay? So in the center state, there is no external force because D is equal to F, they cancel out. So this means constant speed, no change in motion. Blue color means there's a change in motion. Either one is bigger than the other because the forces are unbalanced. This is not a new idea to you. You have learned this in your IG. So when we think about it, right, if we talk about change in motion, there has to be a certain magnitude to describe how difficult it is to change the motion. Okay, so momentum here, we can think about resistance to change in motion. And you will resist your changes depending on your mass and your velocity. So we already know that the larger the mass, the larger the resistance. But also at the same time, the larger the velocity, the larger the resistance. Let's say, for example, there's a car that is driving at 40 km per hour versus a car that is driving 100 km per hour. Which one is easier to stop? Of course, it's the slower car, right? So that one means that when we think about it, when we look at an object and we think, okay, I want to change the motion of the object. I want to harness my inner power or apply a force lah, basically. So if you're looking at an object that is headed towards you, if the object is very heavy, you know it's hard to stop. If the object is very fast, you know it's hard to stop. If it's very heavy and very fast, then GG, it was nice knowing you. Okay. So this means that the how difficult it is to change the motion, because now we want to think about, okay, now no force, no resultant force, motion won't change. Got resultant force, motion will change. But this changing in motion need to be described properly, hence the term momentum. Okay, and physics people very lazy one. We don't want to keep saying mass velocity, so we just go momentum. P is mass times velocity. This is a vector quantity, okay, and the unit will be kg meter per second. I have not written this here, but I've written it in the actual notes that is in the content library. Another unit here is Newton second. Okay, I will explain a bit later. Alright, so since we already introduced momentum, which is a property of an object that has mass and move at the same time, we can now define Newton's second law. Newton's second law tells us or answers the question, how much force do I need to change your motion? So, sure, I have a 20 kg ball ramming its way to me. What do I do? What do I do? How much force do I need to apply? Well, Newton's second law tells us that the resultant force of an object is directly proportional, again, to its rate of change of momentum. So I found out just by marking some of your paper at this point in time in the semester that not all of you are very well versed in calculus, or you might not have even seen it before. If this is you, then my friend, I would suggest that you think about rate of change as how momentum changes per unit time. Okay, so you're going to observe the momentum of a body. Let's say, for example, a ball is rolling towards you, but it's rolling faster and faster. So the momentum is increasing, right? So then you take the increase in momentum, divide how long you observe the ball rolling towards you. Okay, it's a bit like results lah. Change in physics knowledge over how long it took for you to study the physics knowledge. Okay, so this is what it means by rate. So this is the definition of Newton's second law, and as usual, definition is very strict. No other statements will be allowed. Okay, directly proportional to rate of change of momentum means what happened to my good old F equal to ma. This one special condition. Okay, it is not always Newton's second law. So If it's directly proportional, I'm going to insert a constant k and substitute momentum as mv. So this expression will look like this. P is substituted with mv. Factorize the m, I get dv over dt. And I know acceleration is dv over dt. So I get F is equal to kma. Looks familiar, but not really. So before we talk about what K is, we need to define 1 Newton. So when our friend Newton, right, Isaac Newton, came up with all these laws, he decided that, hey, I'm going to call a unit the amount of force needed to accelerate 1 kg by 1 meter per second square. Okay, and you will see why later, because that allows our K to be equal to 1. So 1 Newton here is defined as the resultant force, not the term resultant. Okay, resultant or net force required to accelerate 1 kg by 1 meter per second. So I'm going to substitute into F is equal to kma. So F you put 1, m you put 1, a you put 1. So you get K is equal to 1. No? So you can have your good old F is equal to ma provided your mass is constant, which covers 90% of your past years. The little 10%, what if it's not constant? Well, then you just find the initial momentum and final momentum, you subtract and you divide the time it took for the momentum to change. Okay? I will try a question with you lah. So force here is actually change in momentum over time taken. That's why momentum can have the unit Newton times second. Because if you look at this equation, momentum is F times S ma. So Newton second. Okay. So this one is obviously very useful. Confirm will use one. But you can only do this bearing in mind that force is a vector. And then it has a unit Newton and your mass is constant. And the second one you can use for all cases. Okay? All cases is possible. Alright. So again, just to tell you, the main idea here is if there is no resultant force, either the forces all cancel out or there's no net or resultant force, then there is no change in momentum. Make sense? Your delta P will be 0. Meaning your motion stays the same. No change in momentum, because change in motion is described as a change in momentum. If there's a resultant force, then your momentum will change. Because momentum is mv ma. So normally v will change, but special cases, mass will change together with v. Okay, so we're looking at the change. So if I'm going to just write the F net is equal to change in momentum over time taken, I'm just going to redefine impulse as the change in momentum. So sometimes they ask you to find impulse, which is okay lah. Alright, so from here, net force can be written as impulse over time. Okay, and I guess impulse now can be written as F times T. Hence, you get your Newton second. Okay, so is this important? I think it's all the same equation leh. Everything in this page is just one equation. F is directly proportional to dp dt. If you learn to see physics that way, it's not that hard. Alright, so sometimes we call this impulse. If we want to talk about impulsive force, usually you have a short period of time. Normally we call it collisions lah, which will be the next lecture series. So if you want to find F, you take dp dt, which is the gradient of pt graph. Okay, so if you look back at this equation, net force is dp dt. So dp dt is the gradient of the pt graph. Okay, p divided by t ma. And if I bring this dt over and I integrate both sides, I will get change in momentum will be equal to the area under the graph, under the ft graph. So impulse or change in momentum is area under ft graph. My friends, if you don't do maths or add maths in your lower levels, then you have to memorize this as facts. No? If you know, then it's very basic calculus. Number 1, force is the gradient of PT graph. Number 2, your impulse will be the area under your FT graph. Alright, so it's pretty straightforward. Just try some past years. We shall continue to some examples, I believe. Alright, there we go. Alright, so here you have a ball of mass 0.5 kg thrown against a wall at the speed of 12 meter per second, bounces back at the speed of 8 meter per second. Time lasts for 0.1. So this is actually an impulsive force question. Whenever you want to find force, you can take change in momentum over time. So I will take mv minus mu divided by t. But when I do this, I have to be aware enough to know that u and V are in opposite direction. So if I follow the normal sign convention where I take right as positive, then U will have the sign plus 12, okay, and V will have the sign minus 8. So to find the change in momentum, I will take the final, which is MV, minus the initial MU. Okay, so I just pluck out the M, 0.5, V is negative 8 because it's moving backwards, U is positive 12 because it's moving forward, so negative 8 minus positive 12, divide by the contact time, 0.1. So from here, right, I get the magnitude of my force as 100 Newton. Okay, so here I want to pause a bit because some of you might be asking me, Miss, here got negative leh. Why got negative 1? Alright, so the negative here represents that the force on the ball is to the left because you are taking left side as negative. Okay, but you will be thinking, how do I know that this is the force on the ball? Well, number one, you are taking the change in momentum. So this delta P will be the delta P of your ball. So this MV over MU is all about the ball. So hence, this is the force acting on the ball. So this means when the ball is in contact here, we will experience a force that is in the left direction, like this. This is your force. Okay, that's why you get a negative sign. Next question. Okay, again, the year and the page number is noted there, so you find it yourself lah. So you have a 1.2 kg supported by a person's hand and 2 Newton meter. You remove the hand. What is the vertical acceleration? Okay, so once you remove the hand, the forces will then become unbalanced. So first things first, I'm going to label the force. This is 3 Newton. And then if I read this one is 4 Newton. So you read the balance reading. Second thing I will do, okay, I zoom in already. Okay, I'm going to resolve. Because vertical forces ma. So I'm going to resolve, and then this one have no angle, so 4 sine 37. This one got angle, 4 cos 37. I repeat that for the 3 Newton. This part no angle. This part got angle, so 3 cos 53 and 3 sine 53 respectively. Now just to double check, I believe that the horizontal forces will cancel out. So I press my calculator. 3 sine 53 is 24. 4 sine 37 is 24, 2.4. Okay, so 3 sine 53 is 2.4, 4 sine 37 is 2.4. So this means horizontally is balanced. But what about vertically? So let's take up as positive as down as negative. So up you have 4 cos 37 plus 3 cos 53. And you're going to minus 12 because 12 is acting downwards. So you get negative 7 Newton when you check your calculator. This is the unbalanced force. So then, since the mass is constant, you know the mass here, so I think I can find vertical acceleration using the equation F equal ma lah. So negative 7 will be equal to 12 Newton over 9.81 times A. So 12 Newton is mg lor, the weight. That's why if you want to find m, you take W divided by g. That's how you get 5.7. Newsflash, I think you should know this by now, but for A-level physics, our acceleration... Okay, sorry about that small intrusion. But for A-level physics, as I was saying, all your G has to be 9.81 unless told otherwise. For maths, for further maths, it's 10. Okay, we take different SF. Physics, we will take up to 3 for gravitational acceleration. Alright, next question. You have a lorry. By the way, the unbalanced one, I tend to use the word sigma. Okay, so anyway, a lorry of mass 20,000 kg, constant resultant force acting on it, accelerates from 6 to 3. So you got lorry at 3 meter per second. Lorry at 6 meter per second. And okay, you have a lorry at 6 meter per second and accelerated to 30 meter per second. Okay, so to find the change in momentum, I'm going to take final minus initial, which is 20,000 multiplied by 30 minus 6. Still in the same direction like the lorry. Different than the ball, didn't reverse direction. So this one I get 48000. I actually have the answer as B lah. But if I want to find the force, I will take the change in momentum divided by the time taken, 300, which gives me 1006. Very straightforward. Next question. So in this question, you have a lift situation happening. And the lift, page 13, May, June 13, page 13, paper 13. Okay, anyway, this lift, there's a balancing weight and the passenger car will rise. So what's the magnitude of the acceleration of the car carrying just one passenger? So we know that the balancing weight will go down, okay? And at the same time, the passenger will go up. So I'm going to straighten the pulley, okay? And the reason why I straighten the pulley is so that my acceleration is in one single direction. That way, when I write equation, my equation is easier to write. Let me show you what I mean. Step 2, I'm going to label the forces. So the balancing weight is 640 kg. So I'll take 640 multiplied by g. And the human plus lift is 520 plus 80. So 600 multiplied by g. After straightening if you look at this diagram, after straightening this pulley, I get 640 pointed to the left and 600 pointed to the right. Your acceleration is towards the left. So it's a bit like I take the pulley and straighten the wire. When I straighten this, right, I can clearly decide which one is positive, which one is negative. But let me label the tension first. More about tension in chapter 5, but here you can see the tension will cancel out because it is the same rope. So here, I'm going to use net force or unbalanced net force is equal to MA. And I'm going to remind myself that F and A are vectors, and we need to choose a sign. Alright, so I'm just going to stick to good old right is plus, left is minus lah. So if right is plus and left is minus, I will see that this is 600 G minus 640 G. Okay, this will be equal to the total mass of the entire system because it moves together, right? So it would be the mass of the passenger, the car, and also the balancing weight. Like everyone in Chinese, we call this hampalang, semua sekaligus, everything all together now, we move together. That's why the mass, we are going to add it together. So from here, you will see that I took 600 plus 640. And then multiply by minus A. So the reason why there's a negative A here, very carefully, is because you are accelerating in the negative direction, which is towards the left. Means if I decide to take left as positive, great, then you multiply negative by left and right. Either way is fine as long as you stick to the same direction sign for one particular question. So from here, you can rearrange some stuff. So I'm just going to do it slowly. Here you got negative 40G. Here you got negative 1240A. So I'm just going to find A by taking 40, multiplying by 9.81, divided by 1240. So just be very aware of the sign, okay? Questions can be harder than this. So this one I'll get B lah. Alright, so the last question for the day, I think, would be this guy. Alright, this one is a bit talking to because this is a bit hard, so pay attention. This one will be from May June 16 paper 1-1. You have a man standing on a platform attached to a flexible pipe. Okay, so before I start the question, let me explain a bit about the physics first. The water is pumped through the pipe so that the man and the platform remains at constant height. So basically, if it's constant height, or it's legit means this term lah, resultant vertical force on the platform will be 0. The combined mass of the man and the platform is 96 kg. So the mass of the water that is discharged vertically downwards from the platform each second is 40 kg. So 40 kg, right? 40 kg of water is shoot out of the bottom of the platform for every 1 second. So if you have actually played with a hose before, you will notice that when you shoot out water from the hose, and if you angle the hose downwards, the hose will fly upwards. So like you having water shooting downwards, the man and the platform will be supported upwards. If let's say the man is not moving, meaning the force just nice can support the weight of the man. So now what is the speed of the water leaving the platform? Okay, so we do it one by one. Step 1, zoom in. Step 2, I know net force is 0. And also at the same time, I know that there is a force of the platform, so to speak, pushing the water out. This force is actually a normal contact force, again more in chapter 5. And we know from Newton's third law, I know I haven't tell you what Newton's third law is yet, but then you know, right? Every action has an equal and opposite reaction, Hamilton reference. So Newton said that if you apply a force on me, I'm going to apply a force back at you. So you can see the force of the platform pushed the water out. Then the water said, wow, you push me downwards, platform. the water is going to push the platform and the human upwards. Okay, so if the force pushes the water out downwards, the water will push the platform upwards. Okay, opposite direction. So here you get these two forces. Let's say I label them F1 and F2, and F1 is equal to F2 because this is an action-reaction pair based on Newton's third law, which will be in the next video. All right. So from here, I can tell that, okay, this human will also have some weight. So the W will be equal to F1 because this is on the platform. Okay, so 0 vertical force on the platform as mentioned here, because this is the gravitational pull on the platform. So our system in question, or what we care about, is actually the platform. Make sense? So in this case, if let's say the platform is pushing the water down with F1, then the water will support the platform at F2. Okay, so F1 now will be equal to F2 and also be equal to W for very different reasons. Okay, so you can see that W equal to F1 because F1 equal to F2 because of Newton's third law. W equal to F1 because there is no unbalanced force. And this force, right, when you want to think about F2, this F2 is the force of the platform pushing the water out, which means we will find the change in momentum over time. So what we are saying here is F1 equal to F2, Newton's third law, F1 equal to W, no unbalanced forces, so hence I can say F2 is equal to W. But F2 here is the force of the platform pushing the water, meaning I can take the change in momentum of the water divided by time is equal to the weight of the human. So I'm going to put mg. Now here is where confusion round 2 can happen. So less skilled candidate might look at this and say, cancel the mass. But then these are very different masses, because this mass is the human and the platform, because this is the weight, right? The combined weight of human and platform. And this mass is the mass of the water shooting out. And this V is the constant speed of the water shooting out. Means how do I know the speed is constant? Because all the answer here is constant lah. Alright, so I'm going to pluck out the V. I will have change in mass over change in time. Mass of the human and platform is 96 multiplied by 9.81. So it says that water is discharged 40 kilogram for every 1 second. So you can take 40 divided by 1, make sure everyone is SI. And then you can then find your velocity, and that would give you about 23.5 meter per second. So please go try the questions. This one requires a bit of thinking. Newton's law, right, can be very simple but a little bit counterintuitive because people seldom think about forces. So whenever you see a question, my advice is to think about the forces acting on this thing. What is the change in momentum? How long did it take for the momentum to change? And when you divide these two, you should be able to get the forces. Also at the same time, what is our system? Like in this case, I only care about the platform. I don't care about the water that come out of the platform. I only use the water that came out of the platform, or the changes in the momentum of the water that came out of the platform, because it would just so happen be equal to the force on the platform, which just so happen be equal to the force that support the human. Alright, I think I've rattled on long enough. This is about 30 minutes by now. So take care. Please try the questions, and I will see you in the next video where we talk about Newton's third law. So to recap, Newton's first law, motion will not change unless you apply external force. So got external force, change motion. No external force, no change motion. Second law says that the force that you apply is directly proportional to the change in momentum over time. But that one is not good enough. A-level liao ma. So it's force is directly proportional to rate of change of momentum, i.e. if you have force, your momentum will change. Okay, I think that's all for today, and I will see you in the next video. Have fun trying the next question. Good luck.